Hello, my fellow Almontians, and welcome back to another broadcast from the bunker. We're going to dig a little deeper to the fascinating topic of plate tectonics today. We're going to talk about evidence of crustal movement, faults and uplifting and folds, all sorts of great stuff. So let's get started. Get your do now cranking, numbers 28 to 30. I'll meet you back here in a minute. Okay. So here we go. Classic diagram of the constellations, right? These signs of the zodiac. Sun's in the middle, Earth's going around them. And this, of course, is the annual revolution of the Earth. So here we go. Which constellations are both visible at midnight? So you got to be opposite the sun in the Earth's rotation. We'll point that out in a second. To an observer in New York State, if we're at D, well, here's D. If you're on this side, you can see the sun. That's during the day. And if it's directly in front of you, that's solar noon. But 180 degrees of rotation this way, right, they go counterclockwise, puts you at midnight. So now if you're here and you look out into space, what do you see? Well, it looks like you definitely see Leo. Possibly Cancer, possibly Virgo. Let's see what the options are, but it's definitely got to be one with Leo. So Leo and Virgo looks good, and none of the others have Leo in it. So you got to go with Leo and Virgo when you're on this side of the Earth in midnight looking out into space. You see these constellations here. Okay? Okay. 29... it says the constellations observed from New York State when Earth is at position A are different from position C. And why is that? Well, we'll go back to the diagram here. Position A is over here. Position C is over here. Now, if you're at A and you look out into space at nighttime, you're going to see Sagittarius and Scorpio. If you're at C and you look out at nighttime, right opposite the sun, you're going to see Aries, Taurus, and Gemini. And that's because of the Earth's revolution. Now, if you remember, we did a lab on this in the classroom. You guys had your clipboards. You had to revolve around the room. You rotated away from the light source in the middle. That was the sun, and you saw different constellations. Well, that was giving evidence of the Earth's revolution. Okay? All right, get revolution written in there. The last one, this is a, can't really say a top view, but it's not a side view. We'll call it a top view of the galaxy here. And of course, we live in the Milky Way galaxy. If you remember how far out we are from the center, it's about 2/3, and we're on one of those galactic arms. So whatever diagram they throw at you, it's going to ask you, where is the Earth located? Where is the solar system located? Where is our sun located? It's all the same question. It's going to be 2/3 out from the center on one of the arms. So we're looking at C here, right? It says which letter best represents the location of the Earth's solar system. Well, that's about 2/3 out, right? 3/3 would be all the way out. So 2/3 out and on one of those galactic arms. The arms are a denser part of the of the galaxy there, denser with star clusters. That's your galactic center, and they say that the Milky Way is about 100,000 light years across. Truly amazing, being that the sun's light only takes about 6.5 minutes to reach us from Earth, and that's about 93 million miles away. Imagine how far we're talking now, right? If it took 100,000 years for that light to reach Earth. The distances are beyond our comprehension. Okay, so we're going with C on that one. Any further questions on the do now? You guys know what to do, right? Leave them in the comment section below. Let's jump back to the lesson here. And we'll get the subtitles up. And we're ready to go. So how do we identify crustal movement? A couple of cool pictures here. You can see there's a nice crack right there. All right, we're going to call that a fault. This, you could definitely see some kind of motion there. You'd have to zoom out a little more, but we'll show you some neat pictures that show you evidence that the Earth moved. To try to witness the Earth moving, you'd have to stay in the same place day after day. Be a little boring of a lifestyle, but there are lots of photographic evidence where the Earth has moved. All right. Classic clip here. I don't know if there's any Superman fans in the house. This is a scene from Superman after Lex Luthor set off a nuclear bomb in the San Andreas Fault, right, with the hopes of splitting California off, and he had bought all of the real estate on the land side in the desert. Kind of a funny, crazy story, of course. But anyway, here's the original Superman, little tectonic action. That's Superman's girlfriend right there, right? Lois Lane. Yes, sadly, folks, Superman's girlfriend passed away in that fault right there. But remember, he does manage to change the rotation of the Earth, go back in time, and of course save her life. Not to spoil the whole movie for you, but it's been out for about 40 years. That was the original Superman, right? Christopher Reeve. Yeah, pretty amazing stuff. Anyways, so here we go. Crustal changes. The Earth's crust is constantly undergoing change from major events, earthquakes, mountain building, volcanic eruptions. Make sure you're getting your notes in there. Small-scale changes found in the rock layers on the Earth's surface, such as, well, that's a bend there, so we're going to call that a fold, right? Make sure you get that down. This one, you can totally see a crack in the rock there. That's a fault when you see cracking. And, of course, this one here, you can totally see it tilted toward the sky. That is a tilting. And this is just some evidence that the Earth's crust is dynamic. It's constantly moving. And why is that happening? How does it all happen? Well, the leading theory, of course, is that there are convection cells beneath our feet, right? And, of course, that's being powered from the heat deep within the Earth. Convection, heats up the material. Less dense things rise. It cools down. It sinks. And you get this convection of magma. And that's a lot of material. It's very heavy, and whenever it hits, it's also going to move and make the Earth shudder. So here we go. The crust moves due to these convection currents, right? This is the theory of plate tectonics. They figured this out, or at least they think they did, of course, in the 60s. Prior to that, they weren't sure how it all happened. They had evidence, right? They had the whole Pangea thing, which we'll talk about, but they didn't know how the heck could you make a continent move. But this is the leading theory. Convection cells of magma right below the lithosphere, and plates can go away from each other, they can come towards each other, and when they slam together, you get all this tectonic activity. All right? Well, if none of that motion has happened, well, then rocks tend to form horizontal, so they'll stay horizontal, and they call that original horizontality. All right? Sedimentary rocks in particular form in these flat horizontal layers. We call them strata. And if you see them bent or tilted or even flipped over, then that motion must have happened after it was formed. Okay? Rock layers that are no longer horizontal, we call them deformed strata, and it's evidence of crustal motion. So to be a little more specific on the evidence, right, you have uplift. Literally, rocks can be raised from below, and the distance we're talking about here, folks, is amazing. The tallest mountain on Earth, Mount Everest, used to be below sea level. I know I wasn't there, right? Nobody alive was there. Well, how do we know that? Well, the people that have climbed Mount Everest, over 5 miles high, you can find marine fossils, folks. That's right, fossils of extinct marine life up on Mount Everest. Well, the birds didn't bring them there. All that mostly limestone was formed on the sea floor, and then it was uplifted by tectonic forces. Okay? That's a classic ammonite-looking fossil over there. Rock with marine fossils are found thousands of meters above sea level, right? Case in point, Mount Everest. And this is just some beautiful real pictures of that actual uplifting and tilting. Okay? Tilted rocks are at an angle. They weren't just pushed straight up. The plateaus, as you know, are elevated regions. Well, they didn't tilt. They seem to have horizontal rocks, but they are at higher elevations. So you could get tilting or you could be uplifted straight. Either way, that's evidence of tectonic forces. All right. That's a classic fold right there. You can see it in the picture here, right? These rocks, they form at, different conditions so that if they're very deep within the crust, they get heated. And heated things are a little bit bendable, right? Softer, if you will, and they'll bend. And that's what's going on there. It bent. But if it happens close to the surface, well, then it's going to crack, right? It doesn't have that heat to make it bend easier. It's just going to break, crack and break. All right. So folding rock layers are bent or curved by compressional forces within the Earth, right? Continents slamming together from that convection of magma, moving continents. And it'll turn horizontal rock into folded rock. Okay. Something else to note here. If the fossils found in this rock are subject to intense heat and pressure, they will be destroyed. But if it doesn't get that hot, it's possible to still find fossils in distorted rock layers. If they become metamorphic rocks, well then no, the fossils will get destroyed. All right? Other evidence there, that's your crack, right? That's your fault. And there are different types of faults. I'm not going to go into the details of those. There are normal faults, reverse faults, transform. Either way, it's cracking in the Earth's crust, and the Earth is sliding either past itself, away from itself, but there's got to be a crack involved there. All right, break in the rock along which rock layers are offset because of this tectonic movement. All right, so see if you could tell me which one is which. So hit pause in a moment. See if you could tell me which one is which type of motion. All right, hopefully you have these all labeled. If you made a mistake, no big deal. Just fix it. Here we go. Classic bending like that. Hopefully you wrote the word folding. Over here, it looks like a crack at the surface. Well, hopefully you wrote the word fault. Okay. Over here, once again, we seem to have an arrow pointing in the upward direction. Also seems to be bent. Maybe you wrote two different things here. right? Uplift or a fold would be okay. Here again, we have what seems to be a crack at the surface. That's another fault. All right. Here's a crack going up this way, right? That's another classic fault. And this is a couple things going on. I'm curious what you wrote on that. You could have said tilted. Maybe you said uplifted. It looks like it was uplifted. But beautiful rock strata that used to be horizontal is now uplifted. Take a look at picture B. There was an earthquake, I believe it was in California many, many years ago, where the land actually shifted something like 10 or 12 feet. So, I mean, if you had a fence between you and your neighbor's house, well, now your neighbor's property is your property, or vice versa. Your property is now your neighbor's property. So you guys got to work that out and, of course, do your repairs. If there are gas lines or water lines there, they're going to be cut, which is why when an earthquake happens, cities will often get completely destroyed if it's a big enough earthquake, because now your infrastructure is completely gone. You can't get water. You got gas leaks. You can't put out the fires, right? The water pipes were cut. And it's just a crazy, crazy scenario. All right, couple of summary questions. Which diagram of rock layers represents the best evidence of crustal movement? Well, hopefully you didn't pick the one that has no evidence at all, right? The most evidence here, you got a fault, you have an uplift. That's your best evidence of motion. All right. How can we explain how the crust moves? Well, we said it was that convection of magma, right? The theory of plate tectonics. And we think that that magma convecting, of course, hits the continents and makes it move. All right, so a little introduction for the evidence there. If you do have additional questions, please hit either in Remind or in the YouTube comment section below. All right, take care, folks.